Well, thank you for this invitation to this very enjoyable and interesting meeting. And congratulations to Maxime on his coming birthday, of course. Well, this is a talk aimed at non-specialists, and it'll mainly be about formal differential geometric aspects of sort of Kähler geometry, in particular, the study of things related to Kähler-Einstein metrics and constant scalar curvature Kähler metrics. And as we'll see, certain related objects of differentiometric interest. So let me sort of remind you of the basic sort of setup we want to think about. If we have, say, an algebraic variety with a polarization, the positive line bundle V, we want to, if we consider Hermitian metrics on this bundle, whose curvature form is a positive form, the Kähler metric, so H will be our bundle metric, and this gives a curvature form, say omega H, which we want to assume is positive, then we can we would like to consider the problem of finding an H such that the scalar curvature of this metric is constant. This is the scalar curvature, which of course is the trace of the Ricci curvature, which I'll write as rho. This is the Ricci. We think of the Ricci curvature as a 1-1 form, just like the metric tensor. So this is the general problem of the existence of these things. Can we find such an H? And this is a fourth order partial differential equation for the metric H. H is locally represented by a single function. This is a fourth order partial differential equation for that function. Because we have to take two derivatives to get to the metric, and then the scalar curvature depends on other two derivatives. So a special case of this setup is when the first Chern class of our manifold is a multiple of the first Chern class of our line bundle. But we'll just consider the case when it's a positive multiple there. In fact, we can suppose that they're equal. So we can essentially suppose that the L is the dual of the canonical bundle of V. This is just the Fano case as discussed in a different context in Paul Seidel's lecture. So then we could write down the Kähler-Einstein condition, which is just that the rho is the Ricci form is equal to the metric form. So rho of omega H is equal to omega H. But this can be written in a much simpler way. This thing, which is on the face of it is a fourth order differential equation, just as here, can be reduced to a much more tractable looking second order equation. in the following way, that if we just algebraically, if we have a metric on the dual of the canonical bundle, that determines, a simple algebra at each point, a volume form on the manifold. So H goes to, say, capital omega H, the volume form. That's to say, if a way of saying it would be a metric on this line bundle gives a metric on the dual bundle, so you take a form alpha of length 1 with respect to that metric, and then the volume, the volume element is alpha wedge alpha bar. So this equation here is in fact equivalent to solving just the simpler equation that the volume form omega h is equal to some constant multiple which we can normalize to be 1 to the standard volume form, the sort of Riemannian volume form given by our metric tensor. So this is a second order PDE. So clearly, if you solve the Einstein equation, the Ricci form is a multiple of the metric, when you take the trace, you get constant scalar curvature. A slightly more, a less obvious fact is that the converse is true. If you're in this situation where just the topological conditions you're considering here are satisfied, then any metric with a constant scalar curvature will also satisfy this a priori stronger condition. So let me just remind you of how the proof of that goes. So in case 2, what we always have is a Kähler identity, which says if we take d bar star of the Ricci form, then that's equal to taking d of the trace of the Ricci form, which is just d of s. So if you have constant scalar curvature is always equivalent to saying that the Ricci form is a harmonic form. So maybe so s equals constant is equivalent to rho is harmonic. Well, that's always true, whether in whatever case. The point about case 2 is that in case 2, the cohomology class of rho, which represents the first Chern class of the manifold, is equal to the cohomology class of omega. So by uniqueness of harmonic forms, since the metric form is always harmonic, we can deduce that rho is equal to omega. Once we know the harmonic form in the class of the Kähler metric itself. So actually, in this Fano situation, in a sense, you could study either equation, and you know you're studying. In the end, the solutions are the same, but the framework for the equations is somewhat different. So in this special Fano situation, there's a functional which is important in the theory, which was called the Ding functional. Which is, well, we'll introduce a slight variant as a normalized functional later, but the important part of it is just that we just take, let's say, d naught of our metric h. This is just the logarithm of the integral over v of this form omega h. So it's a very simple thing. If we choose some reference metric h naught, and we write h is say e to the phi times h naught, then this is just so everything our sort of variable is this function phi. Then this thing is just the log of the integral of e to the minus phi. It'll be it works out times omega h naught.
2 phi? Maybe 2 phi?
I think it's all right. I think it's yeah. I should say that this will be a talk with random signs, so probably random factors of 2. So if you get them one right, you might as well get them all right, and that's what will work. So I think that's the right sign. In any case, this is a very simple function. It's just the integral of e to the minus phi. And this was introduced, I think, by Ding in perhaps the 1980s or something, around about then. But relatively recently, it was discovered by Berndtsson, that this function has is convex in a certain sense. So d naught convex in a sense that I will recall later on. And this is a very important point in the theory for reasons I'll try to outline. But I only have time in the talk to just talk about as the formal setup without trying to go into more the analytical aspects of why these things are used. But let's see what's one reason why this Berndtsson convexity is such a good thing is that because this is such a simple functional, it can be defined in situations of very low regularity. We don't need this to be a smooth. Phi can be a long way away from being smooth in order to define this. So the one virtue of the Ding functional, as compared to other things we're going to mention, is that it can be defined in situations where we want to consider metrics of low regularity, or more generally, where the space we're working on is not actually a manifold, but some kind of singular space. The theory developed by Berndtsson and other people working in that kind of pluripotential theory direction extends all these ideas to singular spaces, and that's technically very important. But it's rather crucial, all that extension depends rather crucially being in this sort of second order framework as opposed to this more general fourth order framework. So what the question that this talk aims to answer is how to fit all these developments into a certain standard framework, which I'll explain. We want to fit these ideas into a So that's what I'm going to try to explain, how this can be done. So I should say that actually there'll be minimal new content, in a sense, in what we're going to do. What we're going to do would be looked at critically, say we're writing down Berndtsson's proof in a different notation. But nevertheless, I think it's a point of view. This framework, to me, at least, is a useful point of view which unifies what one's doing with various other situations, and also points, as we'll perhaps be able to indicate at the end of the talk, towards constructions one might not have thought of otherwise related to Ricci flow and similar things. Just also say this is an old manuscript of unpublished manuscript of Graham Siegel, going back to the 1980s, I think, which I managed to not throw away over all these years, which is somewhat related to this. This is in the context of the days when Quillen did a calculation for this kind of Riemann surfaces, complex dimension 1, and then Graham wrote this slightly slicker version. But I don't really have a way of explaining how it's. What I'm going to talk about is directly related to Graham's construction. So I'm not. I say this is really an expository talk. I'm not trying to say that I'm doing anything really exciting and novel, generally speaking. But I hope the point of view may give a way of, especially for non-specialists, to kind of understand some of these things. Okay. So what I'm going to do next is to try to explain indicate what I mean by this standard framework. Standard framework. So what I mean here is we want to consider the standard framework with respect to a group acting on a Kähler manifold, preserving all the structure, both the complex structure and the symplectic structure. So G acts on Z omega, so it's the Kähler manifold by holomorphic isometries. So we should think of, for the moment, think of G as a compact Lie group. In a moment, we'll be extending the ideas to infinite dimensional analogies, but think of this as a omega is the symplectic, the Kähler form on a space.
Before you define omega volume form.
Oh yeah, that's right. Maybe it's a bad notation. What else? Sigma. So forget all about this. Forget all about that. This is just saying we have a Kähler manifold and a group action. So we want to. So the relevant object to recall is that. Under favourable cases, we'll assume there's a moment map, an equivariant map, from Z to the dual of the Lie algebra of G. Which is this is just the generalization of the concept of a Hamiltonian, which would, if G was a circle, say, then we would know that the action would be generated by a Hamiltonian function. This is just the generalization. It's to say, just to fix our notation, at a point in Z we have the infinitesimal action, which I write as say rho sub Z. The derivative of the moment map. The moment map is characterized by saying its derivative corresponds to the adjoint of rho when we identify the tangent bundle with the cotangent bundle using the symplectic form with a suitable sign convention. Then the basic principle in this setup is that on the one hand we can consider the we can consider extending this action to the complexified group. So GC acts holomorphically. On Z. And we can compare what's called the complex quotient, that's to say, looking at the set of orbits of the complex group in Z.
G is a real compact, so G is
Think of it as a compact group. I mean, if this is a fine-dimensional manifold and it's acting by isometries, a compact manifold, it better be a compact Lie group. We will just have to verify that we have the structure piece by piece. But for the moment, think of this as a compact Lie group. So the basic thing is we will compare the complex quotient, which just as a set, this thing with the symplectic quotient, which is given by looking at the zeros of the moment map, which is a G invariant set, and dividing by G. So the general idea is that these things will not be precisely the same, but if we restrict to a set of stable points in our manifold, defines if we leave out some sort of exceptional or bad points in Z, then these things will match up. That's to say, inside the orbit of a stable point, we'll be able to solve the equation mu equals 0 uniquely up to the action of G. So I don't really want to take the time to go into saying too much about, reviewing too much of the detail about that. But just to say, in this situation, there's always a certain convex function, which one is relevant. So fix an orbit, fix a GC orbit, let's say GC times some Z naught in Z. Then we can define a function unique up to a constant, defined by its derivative. That if I, let's use the following notation, if I make a infinitesimal change in Z, given by applying an element like that, it's obvious. I hope that notation makes sense. Then the change in F will be given by the pairing between delta G, or I times delta G, and mu of Z. So essentially we're saying that we rotate this moment map by a factor of I, and then that gives the derivative of a function on GC. But actually this is G invariant, so it induces a function f from the symmetric space GC over G to R. And this always has the property that it's convex from the and the critical, so this is a convex function which you can write down. The critical points, which are just going to be the minima because of the convexity, so the minima correspond to solutions of mu equals 0. So that's to say the problem of understanding this identification. That's the problem of solving the equation mu equals 0 in a GC orbit. Once we fix our orbit, it's a question of understanding whether this convex function has a minima or not. So this is convex in the sense of the geometry of this symmetric space, where it's convex along GD6. With respect to the standard structure. So, for example, if G was SU2, GC would be SL2C. This thing would be, you identify with hyperbolic 3 space, and this would just mean convex. We have a function on hyperbolic 3 space which is convex along GD6 in the ordinary sense. Okay, so maybe that's all. I could try to explain a bit more about the standard picture, particularly the relation with stability, but I think that will mean I don't have time to get to the main points, so I'll just leave it at that. What we would like to identify, we'd like to fix these ideas into a situation where we have a group acting and a moment map, and such that the equation we're trying to solve is the equation that the moment map is equal to 0. Let's leave it at that. And one sort of understands, at least conceptually, how that is related to notions of stability and so forth. So what we want to do is to put, so how can these questions be related to this, be put into this framework? So the first question, involving this constant scalar curvature, this is something which I've been well known for many years. I've given talks about that for many years, but not so much the second question. So that will be what is new in this talk. But let me nevertheless review what one would say in regard to the first question first. And what we want to recall is a bit of standard facts, some standard facts about a homogeneous space, let's call it M, which is the, so let's put it this way. Let's suppose we have a 2n-dimensional real vector space, call it U, with a symplectic form. So let's let M be the set of complex structures, just in the linear sense, on U compatible with omega. So this is the homogeneous space SPNR over UN, because the symplectic group, easy to see, acts transitively on these complex structure, was by definition the unitary group is the stabilizer of the standard one. So all we want to say for the moment is that this homogeneous space has an SPN invariant Taylor structure. the structure of a complex Kähler manifold. So in a few minutes, we'll come back to review more specifically how one can write this down. But let's leave it at that. But except just to say, for example, if n equals 1, this would be SL2R over U1, which is, this is just the hyperbolic plane. So you think this is, in any of the models of either the disk or the upper half space model, the hyperbolic plane. So we're certainly familiar with the fact that this has got a natural Kähler structure. But let's say we'll come back to review more specific formulae in a moment. But let's explain how this stuff fits into our story. Now we'll go to our. Let's take a we take a compact symplectic manifold with a fixed symplectic form, and also with a line bundle, which we'll still call L. So X symplectic, so this is omega compact symplectic. This is line bundle with connection with curvature minus I omega. So let's suppose we have that. Then at each point of X, we have a copy of our sort of our space M given by taking U to be the cotangent bundle of at our points. So we get a space MX compatible complex structures on, say, T star X, and we get a bundle, a bracket underlined M over X with fiber M. So that sections of this bundle are just compatible almost complex structures. Then the Kähler structure on the fibers of this bundle define, at least in a formal sense, a Kähler structure on the infinite dimensional space of sections. Infinite dimensional. That's to say, a picture. We have a section. A tangent vector is given by sort of vertical vector field. If we want to multiply by I, we just use the complex structure on the fibers to do that. If we have two vector fields and we want to define the symplectic pairing, we use the structure on the fibers to define a pairing at each point, integrate over the manifold with respect to the standard volume form of our metric. So let's not write all that down. So that's going to be our space Z in this situation. So of course, that's why I didn't want to try to fit any precise statements, because now we have infinite dimensional spaces. We're just trying to develop the formal picture at the moment. What is the group? So G. This is essentially the symplectic diffeomorphism group, except we'll keep the line bundle in the picture. So G is the group of automorphisms of L as a line bundle with connection, but not necessarily covering the identity map of the base. So such things will preserve the curvature, so in particular they'll give symplectomorphisms. So this is just an extension of the symplectic diffeomorphism group by the circle, by giving the way you lift the action to L. but it means that the Lie algebra of G is the whole space of functions, because we haven't thrown away we don't have to divide by the constants. So this is all tell. Write it in that way. So G matched to S div of x omega, and the Lie algebra of G is the functions on x. So that's good. We're in this sort of standard picture, at least if we're willing to allow infinite dimensional spaces. What you find, indeed, is that the moment map for this maps into. What do you think? This is a space of for volume forms. So the mu. If we identify, if we use the this way, if we use the L2 in a product to identify the functions with its dual. Loose sense, then the moment map mu is given by the mu of J is equal to the scalar curvature of J. But we can, so let's write this, say mu naught. We can always change the moment map by adding an element of the center of our group. So we take the normalized moment map, but mu of J would be the scalar curvature of J minus the average value of the scalar curvature, which is just a topological invariant. So the problem of solving mu of J is equal to 0, that's just saying the scalar curvature is equal to its average value. That's just saying the scalar curvature is constant. So mu minus 1 of 0 is equal to constant scalar curvature metrics. This somewhat slightly ignores some technicalities, but if we want to go back to the problem we were originally interested in, where we want to look at a subset of this. So let's say Z be gamma of M. Set of almost, so we have a subset, say Z, the integrable, almost complex structures. So in fact, for the problem we started with, we're only really interested in the subset given by the integrable, almost complex structures. And so, indeed, we can look at finding the constant scalar curvature metrics as fitting into this framework. Okay, so I want to push on now to get to the main point. So the point is that how do we see in this framework, we don't see anything special about the Kähler-Ein situation. We don't see the Ding functional or anything like that. This is all. So, in the Fano case, we can study a different Kähler metric on this space of integrable, almost complex structures. So let's go back to a review in more detail about our familiar fine-dimensional homogeneous space M. We can think of this as an open set in the set of Lagrangian subspaces of lambda n of our vector space U complexified. We take Lagrangian subspaces in U tends to C. In other words, if we have a complex structure, then we can take these usual space. We have the 0, 1, and 1, 0 parts of the complexification. And these are Lagrangians. What we fix on, say, the 1, 0 space is a Lagrangian subspace. So as such, but it can be identified by the Plücker embedding in the projectivization of the middle exterior power. So we can consider a bundle, say M hat, over M, which is a C star bundle, which is just going to be the corresponding subset of these forms, just essentially the decomposable forms. So this just consists of the forms that are equivalent to, in the standard model, to the decomposable form dz1 to dzn times a constant. So on this middle exterior power, we have a natural Hermitian form, some normalization that comes in depending upon the dimension. So let's define alpha bracket beta so this is Cn alpha wedge beta bar, where Cn is chosen such that if I take alpha, let's call this thing alpha naught, say. So that alpha naught is equal to the standard volume form. So Cn. So we write normalization with respect to dimension. So this then becomes a Hermitian form on this exterior power. So supposing I have an alpha in M hat. So I look at the tangent space of M hat at the corresponding point. That contains alpha. So because this is a cone, this thing contains alpha. So it contains C times alpha. But the basic fact we want to recall is that if we take this Hermitian form, which is indefinite on the big space, if I restrict it to the tangent space of M hat, it becomes negative definite on the orthogonal complement of alpha naught. So in fact, it has signature 1, comma, what the dimension is. So basic fact is alpha negative definite on the orthogonal complement alpha in T M hat at alpha. That's to say, if we have any beta in, I'm saying that in the tangent this thing, then if I remove the component along alpha, which is some formula like this, then that thing is negative and 0 if and only if beta is a multiple of alpha. So this gives one standard way of defining the invariant metric on M. We have this indefinite metric on M hat, but it's negative definite orthogonal to the fibers. So with a suitable normalization, if we normalize by dividing by an extra power of the length of alpha, this induces a metric on M. which will be negative definite with our conventions. So this is a metric on n. And now we can make a similar construction in this infinite dimensional situation. So now let's suppose that C1 of x, with just in the sense of the first Chern class of any almost complex structure, is equal to C1 of L. At each point in x, we're going to have let's write it something like this. At x in, we're going to do the corresponding thing, but tensored with our line bundle L at x. Because if this is projective, we don't care if we tensor our vector space with a one-dimensional space, our space of forms, so defined as above. So we get a bundle, so M fiber X, with fiber this slightly extended space. And this is precisely the condition that there is a global section of this bundle. So it implies the existence of sections. So such things are going to be alpha forms alpha. These are n forms on X with values in this line bundle. Which at each point lie inside this special these decomposable forms. And just topologically, there are such things. But the integrability condition fits in very simply in this way. So say lemma 1 so if we let, say, gamma j hat, what did I call that thing? Z int, I call it. So z hat int. This is the set of alpha sections of this bigger space, where if we can take the exterior derivative on the n forms to find coupling to the connection on L, that this thing is a C star bundle over our previous space. That's to say, if we have an integrable, almost complex structure, which is a section of the space underlined M, we can lift it up to a solution to a section of a form, values in L, in this section of this bigger space, solving this equation, the coupled exterior derivative is 0, and that choice of lift is unique up to an obvious constant multiple. Well, in fact, this just essentially encodes one of the standard forms of the integrability condition. So time is running short, so let me not say anything else about it. more relevant is lemma 2. So let's take now, supposing I have alpha in this. So I have such a form. I can consider the tangent space at alpha of this this space. So this is the tangent space to z int at alpha. So it consists of, so this consists of forms beta, such that they're closed in this sense, and also at each, so the line satisfy the appropriate algebraic condition at each point. So at each point they lie inside the tangent space of the corresponding finite dimensional object. So we'll define a Hermitian form on such a thing, given by just integrating the construction we made pointwise. Well, let's just say it's beta 1, beta 2. This thing is a volume form, so we can integrate it over X. So lemma 2, which is really the crucial statement, is that it's the same statement as we said in the finite dimensional situation. So lemma 2 says that this thing is negative definite on the orthogonal complement of alpha in this tangent space. Yep. So we have this Hermitian form on the space of bundle-valued forms, but which has got no particular, it's completely indefinite. The crucial point that when we restrict to these particular forms, which are both closed in this sense and also because of algebraic condition, then orthogonal to alpha, we have this form becomes negative definite. So given lemma 2, then we, in just the same way as we've discussed before, this metric on this, the total space of this C star bundle induces a metric on our space of integrable, almost complex structures. Just in just the same way as we said before. So from lemma 2, we get an induced, with our sign convention, negative definite, because we can multiply it by -1, the positive, Kähler structure on this space Z int. So the point of the, which is, all I have time is to say the main point and then stop. The point of the talk is that if we use this metric on this one, which this is something we can only do in the Kähler, in the sort of Fano world, but if we use this metric, then we fit into this standard framework in a way which is adapted precisely to the Kähler-Einstein structure. And for example, the Ding functional convexity becomes an example of the general convexity we have in this sort of framework. As I said, that's a bit of a cheat to say it that way, because the proof of lemma 2 is really a disguised form of Berndstson's calculation proving the convexity. So, but I think this is an efficient way of understanding what's going on. Unfortunately, I was hoping to do the proof of lemma 2, which is not very long, but I don't quite have time to do it. Okay, so let's just see what we do have time to do is to see how the moment map comes about. But what is the action? So what is the action of the Lie algebra of our group C infinity of x on, well, first of all, let's take all the n forms with value in L. What you do, when you have a Hamiltonian, what that enables you to do is to give a lift of the symplectomorphism on the base to the line bundle, but you need to multiply in the line bundle by the Hamiltonian. So what happens is that you get the ordinary formula, so let's call it, say, RH of R alpha of H, infinitesimal action. This will be the ordinary formula we'd have involving the Lie derivative. So we take the Hamiltonian vector field, corresponding to H, contract with D of some of any alpha, plus the other thing, D of VH contracted with alpha. But the way the line bundle comes in is now we put in plus IH times alpha. But so in this situation, see, we just got an action on a vector space with a fixed Hermitian form. So it's very easy to understand the geometry. The moment map is just given by, find the right page of my notes. So the moment map. So this is a map from our space. So it takes alpha to the element of the dual of the Lie algebra. So it takes H to just the pairing between this, say, the infinitesimal action R alpha of H with alpha. That's what to do. So this is just the integral of. But now let's specialize to our situation where our form alpha is in the situation we're considering. That means that d alpha is 0, so we lose that term. So we just get d of VH contracted with alpha plus IH alpha, this thing. But now we can integrate by parts to write the term involving this exterior derivative in terms of this, but because d alpha is 0, that goes out as well. So in the end, we just get the very simple thing, the factor of I, which somehow should have been taken away. So in the end, we just get H alpha alpha. Using the facts we know about, well, using the fact that alpha satisfies this condition, that its exterior derivative is equal to 0. So that's to say the moment map, so mu naught of alpha, is indeed just given by the volume form determined by alpha, which unravels into being the correct thing to define with respect to the Ding functional and so forth. So this is quite different, you see, from the moment map in the other situation, which was given by the scalar curvature, which is a much more complicated thing involving taking derivatives. Using this different metric, we get a much significantly different conceptual picture to work with. Right, but I have to stop.
Question? Well, question, yeah. In fact, I had some fantasies years ago, almost in the same direction. Yeah. Gromov theorem that the simple electromorphism group of CP2 is homotopy equivalent to unity group, and it should be kind of thought as analog of Hatcher conjecture that a diffeomorphism group of S3 equivalent to rotation group, and then one can in general ask what a classifying space of simple electromorphism groups. And if I got not confused with science, I thought more about varieties of surfaces, complex surfaces of general type in symplectic sense. And the conjecture is B simple electromorphism group should be modulus space of complex structures on surfaces. Is it?
It should be related, obviously. Yeah,
Exactly
it
this
should be related. Yeah.
Other questions or comments? If not, let's thank Simon again.